Alright, hey everyone. In today's video we want to talk about arc length of vector functions. Now arc length of vector functions is an actually fairly useful idea that we can use. The integral of vector functions was it was good to know, but it's not as intuitive as the area under a curve. But arc length is fairly intuitive. For a vector function, right, we've defined that we can have 3D space and we can have some curve going however we want through it. We might want to know how long it is between that point and that point. Well, we can use arc length to determine how long that curve is. This is something that's fairly important, and it goes along with all of the stuff we've been talking about parameterization over the past few videos. Now, the formula for arc length should be no surprise, really. The arc length for a three-dimensional vector function, or an n-dimensional vector function if you like, would be just continuing this formula. But the length is equal to the integral between b and a, so your starting points with respect to t. So this wouldn't be like your x starting point, this would be your starting point for t, not for x. Of the square root of x dot squared plus y dot squared plus z dot squared with respect to t, and obviously I'm using the dot notation convention that I like to use, such that x dot is equal to the derivative of x with respect to whatever independent variable you've got cooking, whether that be x, theta, or whatever have you. Okay, so anyways, we can rewrite this as the integral between a and b of the magnitude of r prime of t dt, and obviously we can see this because the magnitude is equal to that Pythagorean theorem. Okay, so that's the most general way of putting it, I suppose. Let's try an example. We love our helix, so we're going to keep using the helix for our examples. So I want to find the arc length of r of t equals cosine t, sine t, and t from the point 1, 0, 0 to 1, 0, 2 pi. Okay, so we need to determine from which t's we're going to. Well, we know that the z component is just t, so we look at the z components of each ordered triple, and we can determine what our t value is. So here we have t equals 0, and here we have t equals 2 pi. And you can verify that that works with these other components, but we can look directly from the t as well. All right, so now we want to find the magnitude of r prime of t, and this is just going to be our derivatives squared and then summed. So you get the square root of x dot squared plus y dot squared plus z dot squared. We do this before we plug it in the integral, it makes it easier for us. So we will get the square root of derivative of cosine squared, so we get sine squared of t plus cosine squared t plus 1. Sine squared plus cosine squared is 1, so we got 1 plus 1, which is square root 2. Okay, so now we are left with the length being the integral between 0 and 2 pi, or two t values that bound the interval, of square root of 2 dt. We can pull the constant out and we apply the fundamental theorem of calculus. 0 term cancels out, so we get just 2 pi square root 2. So that is the arc length of our vector function all the way from t equals 0 all the way to t equals 2 pi. So we found the length of one of these helix. So I suppose a biologist could use that when they're trying to find the length of a DNA molecule. They could model it with this helix parameterization, or they probably could just measure it with a ruler. I don't know how the experimentalists work. Anyways, we can move on to another topic. So we also want to talk about the arc length function. Now, the arc length function is a type of accumulation function. So we talked about accumulation functions in Calculus 1. And accumulation functions are really applications of the first part of the fundamental theorem of calculus, which we talked about in Unit 4, back in single variable calculus. So we can define s of t, the arc length, which is a function of the parameter, as being equal to the integral between some starting parameter value and some ending parameter value, which we can move around, so we call that t, of the magnitude of r prime of u, so we change variables, we're not dealing with the parameter anymore, with respect to u, so du. So thus we can make the relationship that ds dt is equal to r prime of t magnitude. So we have a very nice little relationship here. All right, so now we're going to go back to the helix and I'll discuss the helix formula. So the helix formula says that r is equal to cosine of t, sine t, and t. I want us to find a reparameterization for the helix with respect to the arc length as opposed to the t parameter. So to do this, we let t equal 0. So when t equals 0, we know that our point is at 1, 0, 0. That's where our helix starts, down there. So now what we do is we need to find our ds by dt. And we already found that our ds dt is equal to the magnitude of r prime of t, and we found that to be square root of 2 in the last example. So what we can do is we can solve this differential equation by separating variables. So we get, thus, we get ds is equal to root 2 dt, and we integrate both sides. And then we get s of t is equal to the integral between 0 and t of square root 2 du, and u is a dummy integration variable. So then we get square root 2t when we use the fundamental theorem of calculus and evaluate the integral. So now we can determine that s is equal to root 2t, so thus t is equal to s over root 2. So now we can plug this back into our vector function, so we get r of t of s is equal to cosine of s over rad 2, sine of s over rad 2, and s over rad 2. All right, so that is arc length for you. In the next video, we are going to discuss another concept that arises from arc length called curvature, and we're also going to recap all of the different little vectors we've talked about, and we're going to introduce the binormal vector and the tangent vector. All right, thanks for watching. We'll see you next time. Bye.